In this video, our learning objective is that we want to find out the inference. We want to talk about the inference and variances like of the two normal populations. So we have two different situations that we want to compare their variances. Like two populations, and we want to compare the variances. And we don't know the variances, right? So it's like that. It's case 3. I can write down here case 3, but then we have more than one sample. So we have two samples. We'll write down here case 3. So for the hypothesis test, what we do say, we say that we have the null hypothesis, alternative hypothesis. The null hypothesis is that our sigma 1 and sigma 2, they are the same, or the sigma 1 power 2 is equal to the sigma 2 power 2, is like that our standard deviations are the same, or the variances are the same. Our alternative hypothesis is that they're not the same. It's two-sided. If it's a one-sided, we would say less than or greater than. But here is like that. We have like the, we are considering a two-sided here. So these are, like, the parameter of interest is variance, null hypothesis, alternative hypothesis, test statistic. So for the test statistic, here is a little tricky comparing to the, when we have one sample. So when we had one sample, we would use the chi-squared one. Make sure that you understand those concepts very well before coming to this F1, because we use this F1 in the ANOVA table later as well. Like when we are talking about the regression models, and we are talking about ANOVA table, so we would go back to this. But it's good that we learn it here. So for the, when we have two samples, we can't use the chi-square test anymore. We use something that we call it F table. And for the F table, what's happening is that we have two types of the degree of freedom, like two numbers for the degree of freedom, because we have like two samples, right? N1 and N2, so it's going to be two different degree of freedoms for each of these samples. And then we have our alpha. So when we find it, we would say F at the like half of the alpha, for example, for the upper bound, F at the half of the alpha, and then the degree of freedom of these two different samples that we have. So when we are looking at the F table, you will see that we have the like degree of freedom of the numerator, a degree of freedom of the denominator, and then numerator and denominator are this one I'm going to talk about. So what's happening is that when we want to develop the test statistic, we would say that F observed is equal to the S1 power 2 divided by the sigma 1 power 2, and then you would divide it like the denominator is going to be S2 power 2 divided by the sigma 2 power 2. So what we would do, so that's for the test statistic. What's going to happen is that when we are working with the confidence interval, we consider these two that are, we said that the null hypothesis, they're the same, right? So we can say that if the null hypothesis, it was true, so we said that null hypothesis is the one that we don't do anything about. It's like that without any, it's null, it's without any effect, like without adding anything to our system. So that should be true. So we would say these two, the null hypothesis, it says that they're the same. So I would write down the test statistic. It's equal to the S1 power 2 divided by the S2 power 2. So when you're looking at the notes, in the notes, you would see that it's written that test statistic is equal to S1 power 2 divided by the S2 power 2. So I'm going to write down here the test statistic. It's going to be, because my null hypothesis is this, so this is the assumption that we make. So it's going to be the S1 power 2 divided by the S2 power 2. So that's going to be my test statistic. So this is the equation that you would use in your calculation. I just wanted to show you the origin of that equation. What was the origin of it? And then we have the degree of freedom for the numerator, which is the sample number 1, and the denominator is sample number 2. It doesn't matter that which sample you name it as 1 and 2 while you are working with these two samples. Just be consistent with it. Just keep it as number 1 and number 2 for the rest of it. So I have this one. So next step is that I want to make the confidence interval with, because when I have the test statistic, then like exactly the same things that we have with the one sample. So we had chi-square test over there, but here we have F test because we have two samples. And then we will say, okay, now let's see what's the rejection region, again the same. So we would have like with the F table, which is similar, like F curve is similar to the chi-square, so it's skewed. So we would say that our rejection criteria is like that something happened on the left, like the small portion on the left and the small portion on the right that we would have in the curve. And then we would do the, after the rejection region, step number 7 is going to be the calculation. We are going to put all of the numbers, and then we are going to compare it, and we say that, okay, we are going to reject the null hypothesis or we fail to reject the null hypothesis. So that's for the hypothesis part. Next is the confidence interval for the ratio of the two variants. So I would write down, now we want to construct confidence interval. I would write down here on ratio. Over there we said that in case 1 and 2 we said that difference between them, right? So I would say there on ratio of two variances. Okay, so for the confidence interval, if you recall the confidence interval that we had for the chi-square, when we had the chi-square for one sample, we had the chi-square and we had the, like, we were saying that instead of, like, we would say S1, and then we had, like, times with our chi-square, like as a lower bound and then as a upper bound. So what are we going to do here is like that we are going to do something very similar. The only thing is that we would do with the F1. So what I'm going to do here, I would write down like sigma 1, because we said that ratio, right? So sigma 1 power 2 over sigma 2 power 2. So this is the ratio that I'm looking for. And then for the confidence interval of it, of this one, I'm gonna write down the S1, S2 power 2, S1, S2 power 2, and then I'm gonna put down the value of the F. In when we had one case, like one sample, case number 3 for one sample, we would put the n. We had the value of n minus 1 as well, but here we don't need it because we are working with the F table. So I would say S1, S2, and then look at here, I'm going to write down F, right? For both sides, I'm going to write down F times like F. And here is going to be F half of the alpha, right? For the, we said that we need 2 types of the degree of freedom for it. So for the first, I'm going to write down the N2, like whatever in degree of freedom of the denominator, and then degree of freedom of the numerator. So we would read this F value from the table. Exactly the same situation that we have for the chi-square, we have the same situation here. So when we are going with the lower bound, here it was half of the alpha. Be careful, chi-square, like, or F, these are representing from the error, right? It's the variation, so they are not normally distributed. If they were normally, if your error is normally distributed, it means that you didn't consider one of the terms. How is it possible that you have, like, you mean that you can make a model for your error? So if you can make a model for your error, it means that you can add a term to your regression model. And when I say regression model, I mean the mathematical model that we make it, like y is equal to 2x plus, like, 2x1 plus 3 x3. So we are going to learn it in chapter 11 and 12. But here it's like that we would say, okay, so because error is not normally distributed and we have like the skewed one, so here is the F at the half of the alpha, n2 minus 1, n1 minus 1, right, as degree of freedom. I would write down here at the 1 minus half of the alpha, and then n2 minus 1, and again n1 minus 1, like the first degree of freedom of the denominator and degree of freedom of the numerator. So with this, we are gonna write down the, find out the confidence interval. If it was one-sided, what would we do is that we would, for example, consider this one. The only thing is that instead of half of the alpha, you're going to put alpha in your equation. If you are looking for the upper bound, you don't consider this. You're just going to write down your upper bound is S1 power 2 divided by S2 power 2 times F from the table. For reading the F from the table, what would you do is that you would say, I have like the F at the, we are talking about one side. So when it's the one side, it's going to be F at alpha, and then degree of freedom of the first one, degree of freedom of the second, like the denominator and the numerator. So on the back of my book, I have my F table. Let me see if I can show you quickly. Okay, so I try to make it like closer that all of us we can see. So far we worked with the z table, t table, chi-square table. When it was one-sided, the chi-square table, it was like this. Look at here. So it was something like this that you have seen. And then the problem is that now I can't see that. So for the chi-square table, I would say, okay, I have the degree of freedom that I had. I had one sample. So whatever n it was for one sample, I would say n minus 1. So I would have my nu. Look at here, it's written nu. And then I had alpha, right? And I would read the value of the chi-square, and you see it's skewed. So the chi-square at the like half of the alpha, and for the degree of freedom that I had here, and also 1 minus half of the alpha and the degree of freedom of I have here. So that's when I had like the for one sample. So when I have two sample, F table is a little different. We have three different parameters, like variables. One is alpha, the other one is the degree of freedom for the denominator and degree of freedom of the numerator. So when something like that happens, it means that we are talking about 3 dimension. It's not easy to show it in just one table. We have different F tables. For each alpha, we have different. For example, look at here. Here is alpha 0.25. Look at, I don't know, I'm not sure that how readable it is. But as long as you just, because F tables, all of them, they're like this. As long as you could see my hand at how it's showing you the columns and rows, we're fine. And then look at here, I have nu 2 here. Nu is the same as degree of freedom. I told you in some books they show it by nu 2. So it's the degree of freedom here. And then I have the degree of freedom of nu 1 here. And the whole table is for the time that my alpha is 0.25. So what I'm going to do is that I would say, okay, so and it's written here degree of freedom for the denominator. So nu 2, as we said here, is like degree of freedom is n2 minus 1 is for the denominator. It's the same here. So I would say, for example, my degree of freedom of the denominator, like for example, my n2, it's let's say 13. So the degree of freedom of that one, it's going to be 12. So degree of freedom of the denominator is 12. Degree of freedom of the numerator, let's say if it's like, I have like the sample size is 9. So the degree of freedom of for the numerator, which comes from the m1, is going to be 8. So I'm looking for the 8 and 12, right? And then I would read the value of the F. So for example, here, 12 and 8 is 1.51. So 1.51 is the number that I'm going to put it if the half of the alpha, it was 0.25. Then I have it like, for example, look at here, I have it for the alpha 0.25. Here I have it alpha 0.10. So for each of these alpha, I'm going to have a different table. Like I would have it for the 0.05. And then 0.025, and then I can find out the F value for them, like from this table. So we're going to read the F value. So when we read the one thing that is tricky for this one, for case 3 of the when we have more than one sample, is that just how to read this F table, like how to read the data from the F table. So you just should be careful that decide like N1 and N2, it's your choice. Your sample, you would say, this is my sample number 1, this sample number 2, it doesn't matter. Just be consistent with it. If you're choosing sometimes like we say that, okay, so let's say that N1, it's like, for example, for myself, most of the time I would say I'm going to choose the smaller one as sample number 1 and bigger sample as sample number 2. But this is just I know that all the time, that's something that I made it for myself. So you can make it reverse, it doesn't matter. Just something that help you to be consistent with your N1 and N2. When you want to read it, you would know that. So it's like, because F at the like 1 minus half of the alpha at the degree of freedom of the N2 and degree of freedom of the M1, if you reverse the M1 and M2, it's not going to give you the same answer. So it's very important that you would be consistent. Okay, so we talked about the case 3 so far for when we have 2 samples. In next video, I'm going to talk about the case 4, when we have like 2 samples or 2 population and we are interested in the proportion.